Hello everyone, it's me Tabo and welcome to another episode of Coding for Superheroes. So in today's episode, I'm going to be introducing you to Mojs, which is a physics library. It allows you to add real-time physics to your Three.js projects. Mojs is a direct port of the Bullet physics engine. So in today's lesson, I'm going to be helping you to get comfortable. We're going to start by creating primitive shapes and adding rigid bodies to them. Then after that, I'm going to show you how to apply some of the forces to the rigid bodies. And then last but not least, I'm going to show you how to add collision masking to the rigid bodies. If you are new to the channel, be sure to subscribe and make sure that you hit that like button. I appreciate it a lot and it really helps me grow. And last but not least, make sure that you hit the notification bell so that you don't miss out on upcoming tutorials. Okay, so without further ado, let's just jump right in. Okay, so right in front of me, I've got a scene. And this is an example of what we're going to be creating. Okay, so right now I've got a basic Three.js setup. In order for you to participate in this lesson, you're going to need to get the Mojs library file here. So how you can do that is just go to Google and just, if you type in Mojs, then it will bring this up, this GitHub repository. Just click on it and then go to Mojs. Right, just click on build and then this file right here. Okay, this is the one that you need. If you already have your Three.js master folder, then you can also locate it within your Three.js master folder. Yeah, if you want to get it from your Three.js master folder, it is here. You go to Three.js, go to examples, JSM, libs, and this is it over here. So as you can see, this is the one that I am sourcing at the moment. So basically that is all that you need, and then the rest is just the usual Three.js setup. Okay, so first I'm going to start with some global variables that we're going to need. So I'm just going to be copying and pasting them, and then I will explain what everything is doing as I go. So here we're going to be needing our renderer as usual scene. So everything will just be done outside because how we're going to be running this whole application is going to be different to the usual setup. So creating global variables and then accessing them afterwards, because we're going to be using a lot of functions to run the different parts of our program. Like I said, delta time rigid bodies, I don't think I really have to kind of say this out loud. Yeah, just type everything that you see here on the screen. And so inside of our start function here, so basically how we're going to run Mojs, we're going to say mojs.then, and then we're going to call start, which is this function right here. So how that's going to work is that we're going to just create functions which are going to run the different parts of our app. For instance, we're going to set our physics. So we're going to have a function called set physics. Then we're going to set our graphics, which is the Three.js graphics. So we're just going to do everything in different parts. So we're going to run each and every function here up until we get to the rendering part, and then we'll render everything in the end. So this is what's going to be running the whole application right here. Okay, so first I'm also going to create a variable called tmp trans. Okay, tmp trans is over here, but tmp trans is going to be equal to an mobt transform. So this is a transform object. Okay, this is what we're going to be using to basically copy the position and the rotation of our different rigid bodies. Okay, so then first of all, we're going to create a function called set physics. All right, so inside of set physics, we're going to create a variable called collision configuration, and collision configuration is going to be equal to new bt default collision configuration. Now this is basically standard. Okay, no matter what you're doing, you're gonna be setting up this is what you need to ultimately run your whole physics application. Afterwards, we're going to create dispatcher. Now dispatcher is going to be equal to new bt collision dispatcher, and inside here we're going to pass it the collision configuration that we just created over here. Next one is a solver. Solver will be equal to bt sequential impulse constraint solver. Next one, we're going to create a broad phase. We're going to create the new bt dbvt broad phase. And then inside here, we're going to create a variable called physics world. Okay, these are all from here, by the way, just if you're not following All of these variables are from these global variables that I created over here. Now I'm just basically assigning them the different values. So physics world will be equal to new ammo BT discrete dynamics world. So this is pretty much, well, okay, let's just say this is what's going to be running the whole simulation, this discrete dynamics world. Okay, this is our physics world over here. So we're going to pass it the dispatcher that we created over here, and then we're going to pass it broad phase. You have to do everything in this sequence, and then we're going to pass it solver, and then we're going to pass it the collision configuration. Typical gravity is in the y-axis, so we're going to set it to -9. I guess you can set it to whatever you like, but it seems like -9 seems to be somewhat of a standard, but you're free to play around. So after setting that up, let's just then immediately underneath here, let's kind of run that function. I'm just doing this so that we kind of keep track of what we have done and what we need to do next. So after this, I'm just going to run it first. So this is going to be the first function that we're going to run. And so the next function will be to set up our Three.js. So this function will be called set graphics. Now this is just simple stuff, the usual stuff. We're going to create a clock, and then we're going to create a width variable. Okay, so width is basically going to be getting the width property from CSS from our canvas. That's going to be assigning the value of width, and then height is going to be assigned the value of height. And then we're going to create a renderer. Then we're going to pass it canvas, and then we're going to set anti-alias to true, and then we're going to do the usual, set the render size to window.inner width, window.inner height, and we're going to set the pixel ratio to window.device pixel ratio, and then enable shadows. So renderer shadow map.enable equals to true. Then we're going to create a scene, give it some background color, create a perspective camera. We're going to use a point light in this particular project, and then we're just going to set some values for our point light. We're going to make it cast shadows. We're going to set the intensity to 500, and then we're going to add it to our scene. Afterwards, we're just going to position it by 20 in the Y position, and we're going to position it by 1 in the X position. Then same with the camera, we're just going to set it to 15 in the Y position and set it to 40 in the Z position. Then create our camera.lookAt, and it's going to be looking at the point of origin of our scene. So once we're done here, we're gonna also run this function. We're gonna then create our first object, which is just gonna be the floor. We're gonna create a function for that, and that function is gonna be called createBlock. So this is how it's gonna work. In here, we're gonna create an object, basically use this object for our position. So X, Y, and Z will be the different values for our X and Y position. Then we're gonna create another object called scale. This is going to be responsible for scaling our object, and then we're going to create another one called quad. This is just for the rotation. Quad stands just for quaternion. So at the moment, we're going to set it to 0, and we're going to use a box geometry to do that. Okay, so anyway, let me just kind of stick to the flow. Here, we're going to create a mass. Now mass is going to be the mass for our rigid body. Okay, it's going to be using this value. So 0 means kind of set it to static in a way, because it means that there won't be any forces applied to our rigid body when it has a mass of 0. Okay, so it's just going to be still. Okay, so over here, we're going to create our mesh. So we're going to create it using box geometry. Just going to use the default values. And then we're going to create a mesh standard material. Color will be set to random, and the emissive color also will be set to random. And then we're going to add that to our scene. We're going to then set the block to receive shadows. And so over here, we're just going to set positioning and the scaling of our block using these values over here. And then next, we're going to create a variable called transform from the new ammo.bt transform. Like I explained before, this is a transform object. So we're going to be using this to assign position and rotation values to our shape. So first, we're going to say transform.set identity. Then after that, we say transform set origin, and we're gonna use new Ammojs BT vector 3, and we're gonna pass it the values of our position over here. Then we're gonna do the same thing to set our rotation. So we're gonna use the Ammojs BT quaternion, then use the values from our quaternion in here. Then next we create ms, which will be derived from a new ammo bt default motion state, and then we're going to pass it the transform. And then next we're going to create our collision shape. So the shape that we're going to be using here is a box shape, so we're going to say new ammo bt box shape. Then inside here we're going to give it width, height, and depth. We're going to be using again our vector 3. We're going to say scale, and we're going to times scale by 0.5. Now this is also something that is standard, so far that's what I have noticed. So you're gonna times it by 0.5 because I think the scaling of our shape is bigger than that of Three.js. So after we do it, then we're gonna set a margin. Now the margin is for our collision, so setting it to this margin just means that it's just gonna start colliding just a little bit outside of the shape. Okay, it's not going to be visible, it's a small distance. It is meant to avoid the objects intersecting one another. And then next we're gonna create a variable called local inertia. Call shape dot calculate local inertia. So we're gonna pass it our mass, the mass that we created, which is equal to 0 over here, and then we're gonna pass it the local inertia. Next, RB info. So this is going to be equal to new ammos bt rigid body construction info. Here we're going to pass it the mass, we're going to pass it the motion state, we're going to pass it the collision shape, and then we're going to pass it the local inertia. Then from there, then we're going to create a variable called body, and inside of body we're going to create it using new ammo.bt rigid body, and we're going to pass it this info that we got over here. Then after that, we're going to say physics world.add rigid body. Basically, we're going to add it to our physics world. Okay, then so the next function we're going to create is called create ball. So in here, we're going to do pretty much the same what we did here. We're going to create a variable, an object called pos, and it's going to hold our position values. And this time we're going to be using radius and not scale. Give it a radius of 1.5. and quaternion as well, just set it to 0. And then we're going to create our ball using a sphere geometry, and then we're going to use some mesh physics material. These are the settings. You can use any material. Then we're going to say scene.addBall. We're going to make this ball cast shadow, so we're going to set cast shadow to true. Then we're going to set the positioning for our ball using our position object over here. Same with scaling. We're going to use the radius, so it will just scale it evenly on all sides. And then once again, we create a transform, a variable using the new ammo.bt transform. So this process will just be repetitive. Same thing that we did. We set identity, then we set the origin, we pass it the position, we set the rotation, pass it the quaternion values, we create a motion state, we use that, and then we pass it our transform, create a collision shape. This time we're going to be using a BT sphere shape, and then this only requires the radius, and then you set the margin. We do the local inertia again. Also inside call shapes calculate local inertia, we pass the mass and we pass local inertia. So all of this stuff is repetitive, but I'll just repeat it just so that it solidifies in your mind. This will basically make our rigid body to always be active. What happens by default is if this is not set, then when there is no motion, then the rigid body will go to sleep. So after a few seconds of running your simulation, it will go to sleep if there's no movement, no force, or anything being applied to it. So in here, I just set this so that there will always be something happening. Physics world.add rigid body, and then we add the body. And in this case, we're gonna say ball.userData. Now over here, ball is our Three.js object. So inside the Three.js object, we're gonna go to our user data, and inside of user data, we're gonna create a variable called physics body, and physics body will be equal to our rigid body. So once we're done, we're gonna say rigid bodies.push ball. So we've created an array, and this is the array that's gonna hold our rigid body and our mesh. Next up, I will create a function called update physics. Inside update physics, we're gonna pass it delta time. You will see how delta time comes to play. So inside here, we're going to say physics world.step simulation. Our step simulation is going to be using delta time, and we're going to pass it this value over here, 10. So just use 10 as I did. And then we're going to create a for loop. Now this for loop is going to be iterating through our rigid body array. So inside we'll create a variable called obj3. So this will be in a Three.js object basically. So it will be equal to whatever is held in this index. And then next we're gonna create a variable called objammo, and objammo will be derived from the physics body. Remember over here we created this variable inside of the Three.js object. So here we're just going to be assigning objammo to that physics body. So over here, this is the Three.js object. This will be the rigid body. And then next we create another motion state in here. So it's equal to objammo.get motion state. So what we're doing here is we're getting the motion state of our rigid body over here. And then we run an if statement. So we check, okay, if ms is defined, then we say ms.get world transformation, and then we're going to use our tmp trans. If you're wondering what this is, it is the one that this one over here. Okay, so this is the one that we declared right from the beginning. So we're going to be using this throughout. This is what's going to be keeping track of the motion state of our rigid bodies, and it will then be passing that state to our Three.js object. So in here, then we're gonna get the world transform. We're gonna use tmp trans, and then we're gonna say p is equals to tmp trans.get origin. So this will be our position, and then let q equals to tmp trans get rotation. So once we've got that, then we're gonna pass that to our to our Three.js object, which is obj3. So we're going to say obj3.position.set p.x, p.y, p.z, obj3.quaternion.set q.x, q.y, and q.z, and q.w. Okay, so what we're doing now is we're taking the rigid body's position or world position and world rotation, and then we're passing it to our Three.js object. Okay, so now that we've got that, we've got to then create one other function, and this is our render function. I'm just gonna do it right here in between. So inside of our renderer, we're going to be assigning delta time to the clock.delta. And then in here, we're going to run our update physics function over here. Then we're going to pass a delta time. And then we're going to do the usual render.render using our scene camera. And then we're going to run request animation frame. Okay, so now that that is good, let me just double check and make sure that everything else is... Oh yes, I think I might have forgotten one thing over here. Create block. Forgot to actually keep track of this. So in here, we're gonna run our function create block. That's the one for our floor. And then we're gonna run create ball. This is the one that's gonna create our sphere. All right, so let's run this and see if everything is working. All right, one more thing. Sorry, this was a silly mistake. I forgot to also include this. So I need to also render in here. So I need to run this function as well. So please do that and then check if everything is working fine. Another one more thing that I actually please make sure that you have to follow along with this tutorial. Please make sure that you have your canvas set over here. Now I'm assuming that you already know how Three.js works. Now how you run this is up to you. You know what I mean? You actually don't need to do this like this way. You don't have to set your canvas here or create it here explicitly. You can always just do it in here, you know, and just but because of this tutorial and how I created it, I mean, I actually did this a while ago, so this was the format that I was using. So I just changed a few things, but most of the stuff is like working this way. So just also please pay attention to that. Make sure that you have a canvas here, otherwise you're gonna get an error because it's gonna say that canvas is undefined. Run your simulation and see what's happening. Okay, cool. So here I am. Everything is looking okay. I'm just gonna set mine to full screen. So far our simulation is working. So I've got my sphere there, and I'll just run it again. Okay, cool. So far so good. So let's get back to coding. Next, the parts are pretty repetitive because all we're going to be doing is just creating different shapes. So the reason why I did that also is to show you the different primitive shapes that you can create. So far, I know that you can create a cylinder, you can create a cone, you can create a sphere, a box, And then there are also other different shapes like convex shapes. You can also import models and stuff like that, but that's something for another lesson. So in this lesson, we're going to be using 4 different shapes. Okay, so next then we're going to create our box shape. All right, so the next function will be called create box. And yeah, I will run you through this again, but once again, it's all repetitive. So I'm using the position object, using scale object. I'm using the quaternion object. In this particular instance, I'm setting the rotation to this random value, okay, because I just wanted to make it interesting. When the objects fall, then they fall in different positions. And then the mass is equal to 1, because I think I didn't explain. I probably just said it, but I didn't really explain. Like I said the last time, here the mass is 1, so it means that it will be influenced. Gravity will have an effect on the rigid bodies, but if it was 0, it would not. So from now on, all the active rigid bodies are going to have a mass of, so we set the mass to 1. Okay, I called it ball. Doesn't really matter. Ball is a box. Okay, so you can change the name if you want to, but in this case it doesn't really matter. There won't be any clashes. So we're creating a box geometry. This is basically a copy and paste. That's why the names are the same. I just mainly changed the shape over here and the shape of the rigid body. Same material settings as the ball. We make it cast shadow. Then we set the position and the scale. Create our transform variable. We set the identity, set origin, set rotation. We do this again. Our motion state, collision shape. The only things that I'm going to mainly try to focus on is the shapes, right? As to the rest of this stuff, it's just repetitive. So I don't want to waste your time to keep saying the same things over and over again. So in this, what's different here is the box shape. Okay, so this time we should pay attention. This we're using the box shape. And remember what I said the last time, that with the box shape, then you have to multiply it by 0.5. The margin, we do local inertia, then we set calculate local inertia to mass and local inertia. Yes, the rest is all obvious. Once again, we also make this to reset the state to disable deactivation so that it's active all the time. The other use for this is that if you don't want your simulation to be running the whole time, because obviously it's process intensive, then that's what this is useful for as well. Okay, so then yeah, we add our body to our physics world, and then we also give it a variable in the user data property, and then we add that to our rigid bodies array. So I'm just going to highlight the differences only, but the similar stuff I will not be doing so much. All of this, you know. So in this case, the only thing that is different is our cylinder shape. For the cylinder shape, you also use a vector3 object here. This is something that I noticed, that for X and Z scaling, you can leave it as it is. I noticed that for the height, it needs to be multiplied by 0.5. Otherwise, you will just see your object just hovering in the air. And then the rest is all pretty much the same. We do the same things. So next we're gonna be creating our cone. Okay, we're gonna create our cone, and here the difference is just the cone shape. Everything else is the same. Another thing, just the only difference here is that I gave them different positionings, okay, so that they are all not aligned and they fall in an interesting way. Okay, these are the only things, and this, you are free to do whatever you want. You don't have to follow exactly as I'm doing. You can just be free to put whatever values that you want over there. That is fine. You might wonder why I did this with the radius. I will leave it as it is, right? Because I remember that with the cone shape, I had some inconsistencies. So that's why I did this, and then everything was fine. Okay, so just pay attention to these things. So for now, radius times 0.5, height times 0.5. And then the rest is all just the same. So this should be our last shape. So pretty much, yeah, after this, there won't be a lot of other things. It's just small things that I will be highlighting. All the green parts that these are just parts that I will activate to show you then all the other features. Okay, so you can save and then go back to your simulation. Let's see how everything is looking. Excuse me, I'm sorry for that. Yes, we need to run the functions again. Okay. Yeah, my bad. Create ball. So the next one will be create box. Create box, and then create cylinder, create cone. Okay, here we go. So everything is working fine. Now, as you can see, pay attention to this. Okay, even there's a little bit of clipping here. But what I'm going to do now is I'm going to go back and change that radius so that I can try to replicate what I was saying. So over here on our cone, on the radius over here, I'm going to remove this, right? And check it again. You see something is off here. Like this thing is not on the ground. It is just above the ground. But then again, this is, okay, let me just run it again. Maybe I can. Yeah, this is not correct. You can see over here that like this circular part it looks like it's a lot bigger than the shape. So that's why when we come back to this and let's run it. You see now it looks proper, you know. There's a little bit of clipping, but that is actually not a big deal. Like that is not a big deal at all, you see. But yeah. So yeah, at the moment everything is working as it should. So the parts that I need to also then show you is how to apply forces, right? So there are 3 forces. I mean, there are, I guess, many other forces, but we're going to do 3 right now. So it'll be a linear velocity that you can set. You can apply force, and then you can also apply impulse. Okay, we're going to start by applying force. So here I'm just gonna, okay, like this, I just hidden all these parts. So inside of our update physics function, right, just underneath objml, yeah, after declaring this variable over here, then we're gonna just do this. Okay, so we're gonna use this to apply forces to the different rigid bodies. So I'm gonna create a variable called scaling factor, and this will be equal to 3. I'm gonna then create another variable called velocity, and this will be just a vector 3 object, and I'm gonna set z to -1. So this is the direction that I want our force to be applied in. And so we're gonna then say velocity.op.mol. This is basically multiplying. Okay, we're gonna multiply this vector by this. So once we're done doing that, then we're gonna apply the force using the velocity. So we're gonna say objml. Now objml is our rigid body. We're gonna say objml, apply force using velocity. We're doing this over here before this because if we do it underneath here, then the motion state will be inaccurate. So then we do that, and then it will go in here, and the force will just be automatically applied to all the objects. Okay, so as you can see, there is a light force that is being applied to our object, and it's pushing them right over the edge. So that is what apply force looks like. I can run it again just so you can see it again in action or in motion. So yeah, that is apply force. So next we're gonna apply impulse. Now impulse is a bit strong. See, that's what impulse does. So what I can do is I'll decrease the scaling factor over here so we can maybe see it at a slower pace. Let's see what one looks like. So this is like a wind effect, you know, like if you wanted a strong wind in your simulation, then you could apply that force, like a huge storm. Okay, so the next one will be velocity. Okay, so we're gonna think it's set linear velocity. Okay, I'm gonna return it back to 3. Okay, this is kind of slow. I'm just gonna increase it a bit. Okay, let's set it to 10. So this is what linear velocity looks like. Now, I don't know if you've noticed, but the difference between these different forces is that linear velocity, it overrides the natural forces like gravity, for instance. As you can see, like these objects are just being pushed in this direction, but there's no gravity playing or acting on these objects. whereas the other two forces, gravity is still playing its part. So that's the difference between the two. And so next I'm going to show you how to also mask your collisions. All right, so over here, I've created 3 variables. Okay, this is static group. Static group equals to 1. Active group 1 will be equal to 2. Active group 2 will be equal to 4. When I used other numbers, I tried like different ways of using this, and there were some inconsistencies in how it worked. And so I kind of went back to this because this is kind of how I originally learned it. Like the material that I learned from had this setup. I kind of messed around to see if you can expand on it, but it just didn't work. What we're going to do now is we're going to come back here to our, here in physics world, add rigid body. Okay, as you can see, I already had this here, so all I'm going to do is just do that. So how this works is that static group is equal to 1. So what this means is that I'm adding this body to the physics world, and then I'm declaring that this body belongs to this group, static group, which is 1. And then here I'm stating which rigid bodies I wanted to collide with. Okay, so it can be either active group 1 or 2. So that's what this means. And so here with these active rigid bodies, the same also holds true. I'm just going to say this is equal to active group 1, and I want you to collide with static group or active group 2. Same thing over here. It's similar to the previous one. I want it to be in part of active group 1 and collide with these 2 groups. This will be active group 2, and I want you to collide with static group and group 1. Okay, so that's it. So now when we run our simulation, okay, let me remove the forces as the forces are getting in the way. As you can see, they're just intersecting one another. Okay, there isn't any collision between them, but the other groups can collide with one another. If you saw this sphere, it actually collided with that a little bit. Okay, so that's what will happen. So these two belong to the same group, and these also belong to the same group, so they are not colliding with each other. But you can cross change them, you can swap them around. You can say I want the ones that belong to a similar group to collide with one another and with the floor. So you're free to play around with that. So what I'm gonna do here is, once again, I'm just gonna come back and close that. I should have actually done this first. But this is also just another example on the masking of the collision. Okay. So what I'm going to do is I'm just going to hide these for all of them. And then I'm only going to set the collision groups on the plane, on the floor. I'm just going to set it and say I want you to collide with these groups. And so because these ones are not set, what should happen is that all of them should just kind of fall through the ground. Okay, I think that's all set. All right, so let's run our simulation. As you can see, all of them are just falling through. Okay, it's because none of them are set to any of these groups, so this does not recognize them. It's like, okay, who are these guys? What do you want? No, I'm just gonna let you pass. So that's basically what's happening. So yeah, I think I covered everything that I said I would cover. So overall, this is it for this lesson. This is probably a bit longer than usual, but anyway, I had to explain a lot. So that's that. If you're not subscribed, this is definitely the time to subscribe. Hit the like button and make sure that you hit the notification bell so that you don't miss out on some more goodies like this one. So with all that said, my beautiful people, love and peace. I'm out.